In this example, we have three charges arranged in a straight line as shown in the diagram. And the question is, what's the total electrostatic force exerted on that middle charge, the negative 3.4 millicoulomb charge? Well, to find the total force, we're going to have to find the individual forces exerted by each of the other charges in the diagram. So let's start with the plus 1.2 millicoulomb charge. We know that two charges exert an electrostatic force on each other in accordance with Coulomb's law. That electrostatic force is equal to K times the charge of one times the charge of the other, divided by the distance between them squared. Well, K is 9.0 times 10 to the 9th Newton meter squared per Coulomb squared. Now the charges are in millicoulombs. We're going to have to convert those to coulombs to get the units to work out. I'm assuming you know how to do that. So the two charges are 1.2 times 10 to the minus 3 coulombs and 3.4 times 10 to the minus 3 coulombs. Notice that I did not include the negative sign with the charge of the negative 3.4 millicoulomb object. That's because with this equation we ignore the signs. Remember, in physics, signs typically deal with direction, and we're going to figure out direction later with our general knowledge that opposite charges attract and like charges repel. So we just ignore signs when we're dealing with this equation. Alright, to finish out the equation, the distance between the two objects is 1.2 meters. When we work out this equation, we find out that meters cancel and coulombs cancel, so the unit is Newton, and the number is 2.6 times 10 to the 4th. So, the 1.2 millicoulomb charge exerts a force of 2.6 times 10 to the 4 newtons on the negative 3.4 millicoulomb charge. Let's remember that by putting it up there right under the 1.2 millicoulomb charge. Alright, now let's look at the other charge. The negative 4.1 millicoulomb charge is pushing the negative 3.4 millicoulomb charge away. Let's figure out the strength of that force, once again using Coulomb's law. We once again know K, 9.0 times 10 to the 9th Newton meter squared per Coulomb squared. And we know each charge. Once again converting to coulombs, ignoring the signs, we have that one charge is 3.4 times 10 to the minus 3 coulombs, and the other is 4.1 times 10 to the minus 3 coulombs. The distance between these two objects is 2.0. Once again, the meters cancel and the coulombs cancel, and so we're left with newtons, and the strength of the force works out to 3.1 times 10 to the 4 newtons. Let's remember that number as well. Alright, now there are a lot of other forces in the problem, but we're not interested in those because we're just interested in what's happening to the negative 3.4 millicoulomb charge, and these are the only two forces that operate on that charge. Let's now figure out their directions. The 1.2 millicoulomb charge is attracting the negative 3.4 millicoulomb charge because the charges are opposite. So the 1.2 millicoulomb charge is pulling the negative 3.4 millicoulomb charge towards it. And the strength we already calculated, 2.6 times 10 to the 4 newtons. The negative 4.1 millicoulomb charge is pushing the negative 3.4 millicoulomb charge away from it. So its 3.1 times 10 to the 4 newton force is directed towards the left. So we have two forces acting on this charge, both of them pointing to the left. Using the general convention that left means negative, the total force then is negative 2.6 times 10 to the 4 newtons plus negative 3.1 times 10 to the 4 newtons, or negative 5.7 times 10 to the 4 newtons. So, the instantaneous electrostatic force on this charge is 5.7 times 10 to the 4 newtons to the left.